Hello. Nobody's here, I think. So if you do show up or you are here, just say hi in the stream, live chat stream, and then okay, there's somebody watching. So hi, how are you? If you are in my class and you have a question, feel free to ask it. If you're not, if you're just hanging out, hi. There we go, gone. Okay. All right, there is somebody here again. Hi. If you're in my class, say hi. If you're just running around the internet looking for places to chill, that's fine too. If you have a physics question, let me know.
Yo, random dude.
Okay. Well, as we're waiting, I think I might probably start doing some physics because that way I can at least record this and upload it for my AP Physics class. And while we're waiting, maybe for people to show up, I'm going to work on the 2015 free response for AP Physics C, E, and M. Question 1. So here's the question. That's the top part. And the bottom part right there. So 2 people watching right now. If you are actually in my class and you have a question, let me know. If not, you're just hanging out, that's cool too. I'm going to start solving the problem, just to let you know. So I'm doing the 2015 AP Physics C, E, and M. And we're doing free response 1. Okay, that's what we're working on today. Okay, good. So let's take a look. We have the following situation. We have a plate like this. It has a positive charge on it. We have another plate down here. This is side view. This is a negative charge right there. We have it separated by a distance d, as the distance right there. So, question reads, a parallel plate capacitor is constructed of two parallel metal plates, each with area A. So we can just point that out. This and this have an area A and separated by a distance capital D right there. The plates of the capacitor are each given a charge of magnitude Q as shown in the figure above. Ignore edge effects. Okay. On the figure above, draw an arrow to indicate the direction of the electric field between the plates. So here we go. So they're asking us for the electric field. And we have positive charge up here, of course. We have negative charge down here because that's the way it is. It's evenly distributed, and we're going to get an electric field that starts on the positives, goes to the negatives like that. It said just to do one arrow, but I think we're okay doing more than one. And edge effects would, of course, be that there's kind of an electric field curvature at the edges, but we're supposed to ignore that. That's the general shape, and there we go. So on the figure above, draw an appropriate Gaussian surface that will be used to derive an expression for the magnitude of the electric field E between the plates. So we're making an assumption here, the assumption being that we have a constant electric field in between the plates and that it ends there. So we have edge effects here drawn in, but we're going to ignore those and make the assumption that the electric field ends right there. Now, it's really our choice as to how we can draw this. We can make it over the whole thing, whichever we want to do. Might be easiest to do it, so let's just do it like that. So we're going to go have a Gaussian surface that kind of encompasses all of this. Whoopsie. There we go. I'm going to say we're going to ignore those, that they don't exist. So here's our Gaussian. Whoa, that doesn't show up really well at all. So let's use a thicker marker here. There we go. We have a Gaussian surface. Now again, we're really just looking at the side view of this thing. And of course, this thing is going to be coming out as a box, and we're going to make it just the same size as our plate. Okay? It doesn't have to be, but just let's make it that size. And we've drawn that surface now to find the electric field on that. So we're going to ask for finding the electric field in between the two plates. Okay, we can do that. So we're now in part B here. Whoopsie, this is blue. Okay, there's the red one. Here we go. So for part B, we did that. Part B1, okay, we did that as well. We drew the surface. That's all they wanted. And sorry, that's A actually still. That's A1. Then A2 is the Gaussian. We drew it, and now we're going to actually use the Gaussian surface. Oh, hey, Sammy, how's it going? I was just going to get started on doing some physics here, or do you have specific questions? Whichever you want. Okay, Sammy, I'm going to solve the first free response question on the 2015 AP Physics C exam, E&M. That's good. Oh, okay. Let's do that. I'm going to actually take a break on this and switch over to my second board. We can always come back to that, and we can talk about the difference between electric potential energy versus electric potential. Great question. Whoopsie. I should actually grips. Okay, there we go. All right. Okay, Good. So, first of all, we need to kind of just briefly always come back to our 4-quadrant list of things in terms of thinking about what the differences are between those 4 quantities we're interested in. Okay, so we have force, we have electric field, we have energy, and we have potential. Okay, always important. And then, of course, to summarize how they work here. So we have here vectors. These are scalars. Okay, these are properties of particles, and these are properties of space. All right, and okay, and then just how are they connected? Just a reminder. So for electric field, oh, that's crap. Let's use blue. This one's better. So that's also not good. This one's, some of these pens aren't that great. I wish I had Expo pens, but anyway. So F vector is equal to Q E. Okay. Then down here, the relationship is U is equal to Q V. And then in this direction, electric field is equal to minus dV dr, kind of the connector there. And then here, this one is connected in the same way. F is equal to minus du dr. There we go. So we have them kind of connected all together. Okay, so it's always important to come back to those concepts. So in terms of comparing energy and potential, the most important thing to remember is, well, there are 3 things. First of all, they're scalars. Both of them are scalars. That's important. The second important thing is that the electric energy, electric potential energy, is a quality, a property that the charges have. Okay, whereas the electric potential is a property of the space that has that property. If you were to place a particle there, then it would have a certain amount of potential energy. Okay, so hi Saskia, hi Octave. I'm going to answer a question from AP Physics C first, and then I'll come back to Saskia's question. Okay. Ooh, okay, yeah. Actually, I'm going to just quickly answer Saskia's question because I think it's rather straightforward and it's going to be pretty quick. So just hold on, Sammy. I got you started on this, but Saskia, so radio waves, okay, can be used to deliver information to other people, such as sound. So when you turn on your radio, basically light comes to your radio, which is of a low frequency. Okay, so you can't see it, but it comes to your radio and it has information in it, and the information stored in there then is transformed by your radio into sound. So radio waves are light waves, electromagnetic waves, that are very different from sound waves, but they can have the same information stored in them. So in the end, your radio can take that electromagnetic wave and convert it to sound. Okay? So it's kind of like, if you think about the radio wave like a Morse code, like beep 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 beep. That's the radio wave. And then the sound wave is the letters that are come out of that Morse code. So Morse code is kind of like the radio wave, and the written word that is then translated by either a person or a computer, that's the language and that's the sound wave. Okay? Saskia, I hope that makes sense. Okay. Okay, good. Hi, Octave. Good to see you, buddy. We have two people from AP Physics. There's five people in total. My intention is to answer Sammy's question now. Sammy's question was, what's the difference between, just wanted to elaborate a little bit, the difference between electric potential and electric potential energy. And I started that process by reviewing for you guys the grid that is really key to understanding the difference between those four things: electric force, electric field, electric potential energy, and then electric potential. And I wrote the connecting equations in between, and I wrote over here the properties. Electric force and electric field are both vectors. Electric energy, potential energy, and electric potential are both scalars. That's really key for understanding this. Okay, so that's kind of a really, really important starting point to understand what's going on. Now, the question was that Sammy asked for us to expound on what's going on inside a metal object regarding electric potential and regarding electric potential energy. Okay, so let's take that grid. I'm going to erase that. So let's say we've got a metal object. Okay, that's kind of really weird shape. Just to make it a little easier to think about, let's think about a metal sphere. Okay, metal sphere. Metal sphere. Okay, now a metal sphere is made of metal. Well, no, duh. And metal is two things. Metal is stuff and metal is conductive. Both those things matter. Okay, so we have a metal sphere that's made of stuff, which means for a simplistic model, it's plus, minus, plus, minus, plus, minus. It has equal amounts of these two, right? Okay, you get the idea. It's got equal amounts of pluses and minuses all the way through it. Okay, that's the first thing. And that would be true of a non-conducting sphere as well. A non-conducting sphere is also made of stuff, but it's not made of conducting stuff. Okay, now let's see what happens when we apply an electric field to this, for example. So let's say, for example, we get ourselves one of those really, really cool, gigantic capacitors. So we've got a positive plate here, and we have a negative plate over here because we've hooked this thing up through a resistor to a power source, and we let it charge, let it charge, let it charge. We have delta V down here. We've got this thing charge up. Now we have an electric field. Okay. Now the electric field that builds up between these capacitor plates will point in what direction? You can just write it in the stream there, Sammy or Octave, or hey, what the heck, Octave, Saskia, somebody else. What direction does the electric field between these two plates point? To the right. That's correct. So we have an electric field, and we'll do this. We'll draw it in blue. I don't know if this is going to work. Okay. We should have maybe been a little bit. So here's our electric field. Good. So we've got an electric field pointing left to right. And just a reminder about what electric field means. Back to our friend Paul. Paul is a positive charge, as you know, and the electric field indicates the direction that a positive charge would experience a force. So if I had it here, it would be pushed to the right. And of course, that's true everywhere, including inside the sphere. Now, you and I know that in the metal sphere, the positive charges will not actually move, okay? And the reason they don't move is because they're too big. And the electrons are the ones that do move. But for simplicity's sake, we're going to think about the positives and the negatives being able to move inside our metal sphere. So the positives would be pushed in the direction of the field. And because this is a conducting material, they can move, and they will move as long as there's a force. On the other hand, the negative forces, negative charges, we kind of imagine. Here's Nelly. No, wait, Nelly's the North Pole. So this is Norm. Norm gets pushed in the opposite direction. So he gets pushed to the left. So let's see what happens here inside the metal sphere. We're going to get positives getting pushed to the right. And I just move a few of them. 3, and they have to stop moving there. Let's move 4. Let's move another one. There we go. And then also let's move 5 negative charges to the left. 1, 2, 3, 4, 5. Good. And now, of course, what that means is because we've moved charges inside the metal sphere, those charges themselves will also create an electric field. Okay? And if their electric field, though, their electric field points what direction? Now, initially, the sphere was uncharged. Now, inside the sphere, there are more positive charges on the right and more negative charges on the left. So in the sphere, and I'm going to switch colors on you here, in the red sphere, what direction exactly? The electric field points to the left. So there will be an electric field pointing towards the left that's created by those charges. I'm going to kind of pull a fast one on you a little bit because I'm going to put in some more field lines here going from left to right. Okay, now what does that mean? That of course means that inside the metal sphere, the electric field created by the metal sphere is reducing the overall electric field. Because the red field's to the left, the blue field's to the right, the net field gets smaller and smaller as more and more charges are separated to the two sides. Well, what's the consequence? The consequence is that the amount of force that Paul experienced initially is large, but as charges start separating from the two sides, we'll build up more and more positive charges on the right and more negative charges on the left, and they will generate that red field until it gets bigger and bigger and bigger and bigger, and it gets eventually large enough that the red field is exactly the same as the blue field. Because at that point, no more charges will be moved, because then the net force inside here is 0, and therefore no charges will be moved to the two sides. So after this is settled, when this is static or the static or final status, final is that the red field is equal to the blue field. Okay? And of course, that means that at that point, E tot in sphere equals 0. So the total electric field is at that point 0 after a while. It takes some time, though, for this to happen because the charges will not move instantaneously. Once they've redistributed, however, then we have 0 electric field inside the sphere. Sammy, does that make sense so far? Yes, correct, Octave. So the red field will get larger and larger until eventually it will balance out the blue field. So the external electric field moves and separates charges until it can no longer do so. When it can't do so is because their electric field inside the metal is 0. So this is, we're assuming it's a constant electric field. Okay, so the external electric field has to be constant for this to work, because you could, of course, have a situation where maybe there's a current flowing back and forth for some reason. Maybe this is an AC power source. And then, of course, the electric field is changing. And then after a while, I mean, it wouldn't ever settle. but as long as the external electric field is constant, then eventually the electric field inside the sphere will be zero. Now we've established that the total electric field is zero, and that's a good time now to remind ourselves, well, what does that mean? Reminder, E is equal to minus dV/dr, right? That's the relationship that E, the electric field in there, whoopsie, that's crap, sorry. I meant to say this is the vector. E is equal to minus dV/dr times r hat. Well, if E is zero, yeah, no electric field is in the sphere, then what's true of V? Okay, is V, well, what can you tell me about V? So this fact and this fact together mean what? E total is zero. E is the derivative of V, constant, exactly. So V is constant. Okay, it does not have to be zero. This is the most common mistake. So V does not have to be zero in there. It has to be constant. And that's a good time to remind ourselves a couple things about these two. Namely, V is going to be continuous. Continuous means that the value of V at any point is only one value. It doesn't matter whether you come from one side or the other. It's a certain number, and that number is not going to be different if you scooch over a little bit. And why is that important to distinguish? Well, this is not true for the electric field. Okay, for the electric field, if we look at this, like if we're going along this, we have constant electric field along this line, right? And then we get here, and boom, it's zero. Right there, it's zero. Here, it's constant. Zero, 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 constant. Okay, so we made a graph of this thing right here. Okay, we would have an electric field that is constant, jumps down to zero, stays zero, jumps back up to that constant value. Okay, so electric field is not continuous at all, it's jumpy. But V has to be constant, okay, in here. So it's a certain value there, and all the way the same way all the way through here. Okay. Okay. So that's what would happen for a metal object inside an electric field. That was Sammy's question. Okay, and of course, if we have this object inside, this object being a non-conducting sphere, such as styrofoam or something else, then we wouldn't get the same effect because it can't quite do this because the charges are not free to flow. Again, we're making an approximation here that when we say conductor, we basically mean perfect conductor. And when we say insulator, that it doesn't conduct. But of course, in a non-conducting sphere, there would still be some charge separation or charge alignment. So for example, in this case, maybe the positives can't go all the way over here, but they could kind of turn themselves. So if you think about, for example, a polar molecule like water does this, it has a plus side, a minus sign, it kind of turns itself in the presence of an electric field. And the same thing would be true here, where there would be a slight alignment, which wouldn't be the same thing as canceling out the electric field in here. That's not going to happen. Okay? Sammy, does that make sense? Okay, I'm not sure who's still here. We have 4 people viewing, okay? And I don't see any comments come up. 3 people are viewing now. Okay, would V not be constant then? Correct, yes. So let me ask you the other way around. If V were constant for non-conductors, what would be true of the electric field?
Yeah. Hello? Yeah.
Ben, you can't be here, Doodle. I'm on a live stream. And you are doing something important or not? No. So get off there. German Arbeitsbuch is what I said, Benjamin. The whole book up to page 42, which is due tomorrow.
It's not due tomorrow.
Friday? It's due Friday.
That's due Friday.
Really?
There's no due date.
I'm on the live stream. It's due after break, which is the 20th of April. Oh, what? So if V were constant, then the derivative of V would be 0, and then the electric field would be 0, which it's not. The electric field is not 0 because the electric field that we're applying, the blue one, is going to be much stronger. The net electric field will be towards the right, okay? So the electric field will be to the right. Okay. Okay, does that make sense? Oh, I see it. You mean the capacitor. Pretty much. There will be some realignment, okay? And just even a slight realignment might still create some electric field, but it's going to be pretty much the same, okay? Because otherwise the electric field would be 0. Okay? All right. Hey, maybe it's a good opportunity for me. I don't know. We could do something different. Other questions? Octave, are you still there? Do you have a question? Is somebody else here? Is somebody non-AP here, maybe? Okay, I don't have any other people saying hi. Octave was here earlier. Does he have a question, or does Saskia have another question? Makes sense. Okay. Anybody else have another question? Saskia? Maybe you already logged out. I'm not sure. I can't tell who's here. I just know that 4 people are here. Oh, hi, Rhea. How are you doing? Did you have a question? Or just hanging out? That's cool too. Okay. Okay. Good. So earlier on, I talked about using a Gaussian surface to find the electric field between 2 capacitor plates. We could go back there and try and do that. It's actually pretty straightforward exercise, I think, relatively speaking. Just a reminder, we have a capacitor plate that's positively charged, a capacitor plate that's negatively charged. The electric field points down from the positive to the negative side, and we've decided to put our Gaussian surface in like this, and realizing that, of course, this is just a side view of effectively kind of like a shoebox that comes out and actually is, in this case, before and behind the board, and it encases the entire plate here. Okay, and if we look at that, we can figure out how to apply Gauss's law there. Okay, and specifically, Gauss's law, of course, is that the integral EdA is equal to the enclosed charge divided by epsilon naught. Okay. And the electric field is constant all along here. And of course, the electric field pierces this surface exactly over the entire area A of this thing. Okay, so we can say E times A, and it's a constant electric field. There we go. Okay, is it? And that's equal to the enclosed charge, which of course is plus charge. There we go. Divided by epsilon 0. All right. So that means that electric field is equal to Q divided by A epsilon naught. There we go. Pretty straightforward, actually, right? So that's all we're doing. Electric field is Q divided by A epsilon naught, and you're good to go. Okay, and if you look at that, We actually get pretty quickly. Hang on, let's leave it at that. Okay, so that's that problem, and that finishes problem A of that test. Okay, is there any other question? I can keep going on that problem. Yeah, I'm good. For our assignment where you said TBA due Friday, are we supposed to do the worksheet that's attached to the FET submission, or what do you want us to do? Hi, Rhea. This is for the 9th grade optics FET simulation. I haven't set that up yet, and I will give you an assignment that'll have a small project for Friday, the first step. But I'll split up basically this lab report into like 3 parts, and the smallest part will be for Friday, and then the other 2 parts will be after break. But I will still post that this afternoon. Right. Attached to the FET. No, don't. I'm going to do my own document. Correct. So don't do the document. They have several online, but I want to have you do specifically what I'm asking you to do. And I think there's too much stuff in that. They have different worksheets on the FET simulation website, but I think they're too big. Okay, cool. Okay, anybody else here? We got 4 people. There we go. That was question A. Let's take a look at our sheet. So there we go. Okay. Good. The space between the plates is now filled with a dielectric material. Oh, isn't that fun? That is engineered so that its dielectric constant varies with, oh my God, are they crazy? Oh, I love this. This is so insane. Okay, they have a dielectric material that is not constant. Damn it, Janet, that's awesome. Okay, I'm not going to attempt that right now because that's going to be messy. But they have a dielectric that changes its dielectric constant as a function of position, which is completely nuts and unrealistic for any physical situation. So, but we can do it. It's going to involve calculus, obviously. Okay, so we're not going to do that right now because that seems kind of crazy. Okay, so yeah, that's part B. That's crazy. I mean, yeah, it's nuts. So they put this stuff in here, and it varies in its dielectric constant. And the dielectric constant would have a tendency to change the electric field. And because the dielectric constant is not constant, shit, what is wrong with these people? Okay, it has different values, and it varies continuously, which is the crazy thing. It needs to continuously change as a function of position in order for the electric field to be a very specific function that actually has an exponential in it. Oh, no. What we're going to do is this. I'm going to do it with you. I'm going to do this problem with you guys tomorrow in class. Okay. But you guys have a good head start with part A. At least you've reviewed that. I think that's always going to be helpful. But if you guys don't have any other questions, I think I might just, end the live stream here if that's okay with you guys. And then I'll see you guys in class tomorrow. Is that cool? Yeah, don't skip it. That's not a good idea. Okay. Good. I'll see you tomorrow. We'll do that problem tomorrow. It's a little nuts, but yeah, I'll do a few stretches before to make sure I get it right. Okay. I'll see you guys tomorrow.